All right, and hello everyone. Our speaker today is Professor John McCarthy from Washington University in St. Louis, who will speak on the isometric extensions.
Well, thank you very much. Thank you all for coming. I'm sorry we're still doing this remotely. Hopefully that will change. So the topic of the week was on interpolation. So how's what I'm going to talk about related to interpolation? Well, a typical interpolation problem is you're given two sets, a big one omega and a smaller one v, and then you're given a space of functions on v, let's call that x, and another one on omega we'll call y, and then v is often a discrete set, and then given a function f defined a priori on v, you want to find an extension to y, a function on the larger set omega whose restriction to v is f. And then the sorts of questions you ask are, can you always solve this? If so, what's the best constant so that the norm of the extension is less than or equal to that constant times the norm of the original function? And then for any particular f, you can ask, what's the best extension in the sense of the one of smallest possible norm? And then a common phenomenon is that the best extension, the one with smallest possible norm, often has extra regularity than you a priori have a right to expect. It has extra regularity than it gets from just being a function in y. The fact that it's the smallest extension forces other things from variational inequalities and the like. So I want to talk about a kind of a variant problem on this, which says, suppose you know you can do this extension, and moreover, you can do it in the best possible way, that your constant is always 1. What does this say about the Banach spaces x and y and how they're related to each other? Or if you like, what does it say about the sets of v and omega and how they're related to each other? And depending on the setting, of course, this may not be very much. The teacher extension theorem says that if I have any continuous function from some closed subset of a normal space into the unit interval, I can always extend it to the whole space without increasing the norm. So you get it for every possible x. There's no restriction. However, continuous functions are obviously much more malleable than holomorphic functions. So if you look at holomorphic functions, then restrictions start popping up. So let me tell you a little bit about the prehistory and why, sorry, I forgot to say at the beginning of the talk that this is joint work with Jim Agler and Łukasz Koszynski. Why we first started thinking about this problem. And the origin was in trying to understand pick problems on the bidisk. So a pick problem on the bidisk is, and I'm never quite sure how to draw the bidisk. I normally draw it as a square, but Nicholas Young, who's not only has beautiful handwriting, he's also a good draftsman, has a much more elaborate picture that kind of shows it cylindrical in some directions and flattened in others. So this thing here is my attempt to draw a cartoon of the bidisk. So for the pick problem, you're given a finite number of points here sitting inside the bidisk, and then you're given some values they're supposed to take in the plane. And then you ask so you can always solve this, you can solve it with a polynomial. So then you ask, what's the smallest possible h infinity norm of a function that solves your interpolation problem? So your interpolation problem here is on a finite set. And so it turns out that there are two qualitatively different situations that can arise. Either your original data has a unique minimal norm solution, Or it's not unique, but there is a there is a one-dimensional set, a variety, on which all the solutions coincide. So that's what I've drawn here. This U here is the uniqueness variety. Every solution, so the original problem has more than one solution, but they all agree on U. And moreover, the supremum attained on U is the same as the supremum on the whole bidisk. So then we wanted to know, does this say that U is special, or that the function phi restricted to U is special? In other words, if I take any function on U, should I expect it to, any bounded function on U, should I expect it to extend to a bounded function on the bidisk with the same norm? Or is the fact that the function phi came from a, yes, so this is a one complex dimensional variety in a two complex dimensional space, Paul.
Thank you.
You basically, if you take more than one solution, you look at the zero set of the difference, that'll give you complex sheets. And then you intersect all those and you're left with turns out you can't end up with a zero dimensional variety. So if it's not the whole thing, it's one dimensional. Or is there something special about the fact that the phi came from an interpolation problem, which enables you to extend them without increasing their norm? So that's the background. I'm not going to talk more about this problem. I just want to say why this trying to understand what it means to say you can always extend without increasing the norm. Why we got interested in that. So now let's go to the more general problem. So I'm given some set omega in D complex variables, and I'll let O of omega denote the holomorphic functions on omega. I've often wondered why O is chosen. Maybe it's more natural for French speakers who have holomorphic functions. And then we have some analytic subset V. Let's give it a different color. So V is some sort of set like that. And an analytic subset means that locally, V is defined as the zero set of the intersection of the zero sets of some functions. So locally, given any point, I can find some neighborhood, and on that neighborhood, V is just the zero set of some set of functions on the neighborhood. So it's a relatively nice set, though it is allowed to have double points and algebraic singularities. And then we want to know what it means to say a function is holomorphic on V. So we say a function is holomorphic on V. Again, that's a local definition. Saying a function is holomorphic on V says I choose some point, I choose some little neighborhood of that point, and I want to be able to find a bona fide holomorphic function of D variables whose restriction to this little slice of V here intersect that set agrees with our original function F. Okay, so that's just the definitions. And then the first question is, if I have such a function, so I go back to, here's omega, and here's V. Oh, sorry, V had a hole in it, didn't it? A curve in it. Let's make V more exciting. Here's V. And now you're given some function F defined just on V. Can you always extend it to be holomorphic on all of omega? And the answer to that is yes. This is a theorem originally due to Henri Carpin in 1950. So I said omega was pseudo-convex. That just means it's a domain of holomorphy. And Cartan showed you can always extend functions that are locally holomorphic on some analytic subset to the whole set. This is quite a hard theorem to prove. But we're going to ask a little bit different question. We're going to say, let's assume our original function is not just holomorphic, but bounded. Then I want to know, can I extend this to a bounded holomorphic function on the whole set? And can I do this in such a way the norm doesn't increase? So we're going to specialize to the case where omega is the bidisk. So in the bidisk, the question becomes, here's the bidisk. And then I choose some variety V inside the bidisk, say this one here. And I have some function f defined on V. And then my question is, so f is bounded. So let's say f maps into the U. Saying it's bounded says it maps into a disk, so suppose it maps into the disk of radius 1. Can I extend f to a function phi on the whole bidisk that also has norm 1? So does there exist a phi that extends f and has the same norm? And this is going to turn out to depend on what V you choose. So for example, if I chose V to be the this cross here, Z1, Z2 equals 0, then it turns out you can't do it. And there's a fairly easy way, a fairly easy example to see that doesn't work. If I take, if I define f, so f is just defined on V, this red cross. So V is just two intersecting disks. They intersect at the origin. So on the horizontal disk, I define f to be Z1. On the vertical disk, I define it to be Z2. That's a holomorphic function. It's obviously holomorphic everywhere except at the double point. And to see it's holomorphic at the double point, you just observe that in the neighborhood of that double point, it agrees with the function Z1 plus Z2 restricted to V. So it is holomorphic. And it has norm 1 on V. But if f extended to some function phi from the whole bidisk, I've told you, by virtue of telling you what happens along this horizontal disk and the vertical disk, I've told you not only does phi map 0 to 0, but I've told you what its gradient at the origin is. The gradient has to be 1, 1. So the norm of the derivative of the origin is the square root of 2. And this will contradict Schwarz's lemma for the bidisk. So the singularity in V enabled us to define a function that had norm 1 on V, but because we forced its, we were able to control its derivatives in two different directions, we're going to, that means that if I did try and extend it, if I think of the disk here, Z1 equals Z2, which lives inside the bidisk, I forced it to be a holomorphic function on this disk that sends 0 to 0, and whose derivative of the origin is the square root of 2, which just contradicts the one variable Schwarz lemma. So singularities in V are bad. Now, in general, the answer to question 2, even for the bidisk, is not known. Which subsets have the isometric extension property? The fact that the property that every bounded holomorphic function extends to a function with the same norm in H infinity, the bidisk. However, if you assume that V is reasonably nice, for example, it's algebraic or it's polynomially convex, then it only has this isometric extension property in a very rigid circumstance. It has to be a retract. So what does a retract mean? If I take some set omega, and a retract of omega is some set V, such that there's a function R from omega to itself that that maps everything onto V. So the formal definition given here, there's a function R from omega to V, which is holomorphic, and it leaves V invariant. And it's completely immediate that if you do have a retract, then it always has the isometric extension property, because given any function f on V, I can always give you an extension to the whole set by just looking at f composed with the retract R. So that'll always have exactly the same range as f. What does it mean to be polynomially convex? I mean that the closure of V inside the closure of omega is polynomially convex. I.e., if I take if lambda is any point in omega closure such that P of lambda is less than or equal to the super P on V for all polynomials P, that implies that lambda is in V closure. This is polynomially convex.
Thank you.
And R has no R has no effect on the norm of phi, because the range of phi is exactly the same as the range of f. So since the range of phi is the range of f, the sup, so we're just looking at the sup norm here, so the sup norm will be the same. Did I get all these questions I'm missing? Yeah, I think I've got all the questions.
Thank you.
Thank you for asking questions. It makes me realize that at least one person is paying attention. Two different people have asked questions. That's two more than my normal talks. And so retracts always have the isometric extension property, and retracts are well understood in just two cases, the ball and the polydisk. So in the polydisk, there's a theorem of Heath and Suffrage, which says the only retracts of the polydisk are graphs. So that means up to a permutation of coordinates, an m-dimensional retract of the polydisk in d variables is just the graph of some function psi that maps the m-dimensional polydisk to the d minus m-dimensional polydisk. It's just the set of all points of the form z psi of z. And then your retract is kind of obvious. You take R of z1 through zd to be z1 through zm, and then psi of that. So it's obvious that any graph like that will be a retract, and they proved that those are the only retracts. So at least in the bidisk, polynomially convex sets that have the isometric extension property have to be retracts. Is this true for more general domains omega? Having this isometric extension property seems to be a very rigid restriction to put on the pair V omega. And so sometimes the answer is yes. I just told you it was true in the bidisk. It's also true in the ball in any number of variables. And it's true if you take a strictly convex set in 2 dimensions. So strictly convex means that at every boundary point, there is a tangent plane that just grazes that point and no others. And so Łukasz and I spent quite a lot of effort trying to prove this in with more and more relaxed conditions on omega. But this turned out to be a bit of a fool's errand. So if omega is the symmetrized bidisk, which is not a convex set, Agler, Lykova, and Young gave an example of a subset that has the isometric extension property, an algebraic subset, but is not a retract. And then there's an even simpler one. If I take omega to be the diamond, which I'll call D, that's just the set of pairs Z1 and Z2, such that the modulus of Z1 plus the modulus of Z2 is less than 1. So this is a convex set, though it's not strictly convex because it has flat edges. Then again, having the isometric extension property does not force it to be a retract. So to give you a feel for what's going on, I want to analyze this case with a simple example. So our set V on all 3 occasions is going to be these 2 cross disks, D cross 0 uniting 0 cross D. And that lives inside, and so I'm going to think of 3 different omegas. In the first case, it's the bidisk. The second case, it's the ball. And in the third case, it's the diamond. And I claim that for the first 2, we do not have the isometric extension property. And in the third one, we do. I want to show you why. So for the first 2, Schwarz's lemma is what rules it out. So Schwarz's lemma for any balanced set says that if phi is a holomorphic function from omega to the unit disk that maps 0 to 0, then its linear part, the derivative of phi at 0, also has to map omega to the unit disk. And let me recall, if it's a while since you took functional analysis, that you say a set's balanced if it has the property that given any point in the set, if I multiply it by any complex number of modulus less than or equal to 1, that stays in the set. So it's circular in some sense. Given any point, it contains not only the circle through that point, but also the disk through that point. So with Schwarz's lemma, you can rule out the first 2. We already really talked about this for the bidisk, but we take the same function, f of z1, 0 is z1, and f of 0, z2 is z2. This has norm exactly 1 on this cross, t. And because we're in 2 dimensions, and I've told you at the origin, I have 2 intersecting sheets, I know what the partial derivatives have to be in both directions, so I know everything about the derivative at 0 of any possible extension phi. The derivative of phi at 0 has to be the 1 by 2 matrix 1, 1. And then it's easy to check that 1, 1 doesn't map the bidisk into the disk. For instance, it doesn't take the point 1, 1 doesn't get mapped inside the disk, and it doesn't take the ball into the disk either. If I take the point 1 over root 2, 1 over root 2, that'll get mapped to the number root 2, which is outside the unit disk. The Schwarz lemma doesn't rule out the third example, because if I take any point in the diamond, well, because the modulus of z1 plus the modulus of z2 is less than 1, if I multiply z1 by 1 and z2 by 1 and add them up, I still get something less than 1. So the Schwarz lemma doesn't rule out the diamond. And in fact, you can use the Schwarz lemma to prove that the diamond and with these two cross disks in it does have the isometry extension property. And it's a simple proof, so I'll give it to you. So let's first assume that the function you want to extend maps 0 to 0. And then without loss of generality, you can assume it has norm 1. And then you'd find the simplest possible extension. So my G is a priori just given on these two cross disks. And I want to find a function on the whole diamond. So I define my function on the whole diamond just by saying it's the sum of G evaluated on the first coordinate plus G evaluated on the second coordinate. This is certainly holomorphic. We need to check that it's bounded by 1. And this is true by Schwarz's lemma. Because if I look at the modulus of phi of z, by definition, it's this sum G of z1, 0 plus G of 0, 2. And G of z1, 0, so G maps on the horizontal disk. It maps the horizontal disk to the unit disk. It maps the origin to the origin. So by Schwarz's lemma on the horizontal disk, I get G of z1, 0 is less than or equal to z1, modulus of z1. By Schwarz's lemma on the vertical disk, I get that the modulus of G at 0, z2 is less than or equal to the modulus of z2. And the fact we're in the diamond says the sum of these two is less than 1. So the simplest possible extension works for functions that map 0 to 0. And if they don't map 0 to 0, we use a linear fractional transformation to move things around and get over that little problem. So with for the diamond, you do get that these two cross disks have the extension property, but they don't have it for the ball or the bidisk. Now, from a local point of view, this is pretty surprising because it's the same variety. So the difference is somehow something global about the open set omega in which the variety lives. So that led us to shift perspective. So our original problem, which I'll call problem A, was you fix omega, and then you try and find all analytic subsets V such that the pair omega V has the isometry extension property. And we were led to, in that case, showing that often case this forced V to be a retract. But now we're going to go the other way around. Suppose I take a set which I know can't be a retract. For instance, these two cross disks. Retracts always have to be smooth. So a set like this can't be a retract. And I ask, for what omegas, if I fix that and now I try and draw my omegas, can I find some omega maybe like that, for which the pair omega V does have the isometry extension property. And this shift in perspective, well, the first thing you can ask is, what does V have to satisfy that there's any such omega? So we've shown you can do it for two cross disks, but suppose I take something really funky. I take something that has a cusp and say a double intersection. So I take some algebraic set that looks like that. When I intersect, so I cut it off. I take a chunk of an algebraic set, which looks like that, is it possible that I can find some omega containing this set V so that I have the isometry extension property? And the strange answer is that there's absolutely no restriction on V. If V is any analytic set, so to be an analytic set, you have to define it inside some domain of holomorphy, because you need to define it with respect to locally holomorphic functions. But if you're given any set that's an analytic subvariety of any pseudo-convex set, then you can always find some domain of holomorphy omega. So even if we go back to this weird example here, I can find some omega. It may be a very small set going around it, but I can find some omega so that the pair omega V has the isometric extension property. No restrictions at all on V. Well, whether there's a restriction depends slightly on what you consider a domain of holomorphy to be. So if you're a follower of Hormander, domains of holomorphy do not need to be connected, and then the theorem is true as stated. However, if you believe that a domain ought to be connected, then that comes as a kind of a trivial condition. So if you want omega to be connected by definition, then V has to be 2, and that's just the maximum principle. So the difference between those two is just what you consider a domain of holomorphy to be, or a pseudo-convex set to be. I tend to favor domains as being connected because in one variable, that's what a domain is. But people who start in several complex variables by reading Hormander, he doesn't want them to be connected. Okay, so that's pretty weird that you can always find some omega no matter how nasty V is. And let me just point out that most sets, including, for instance, these 2-cross disks, aren't retracts of anything. So despite all our efforts to connect the isometric extension property to retracts, in the absence of convexity, retracts seem to have very little to do with the isometric extension property, which I found extremely surprising. So let's analyze the 2-cross disks again, and now we're going to ask, suppose I want to find all sets omega so that the pair omega T has the isometric extension property. Well, in some ways, the diamond is the maximal such set. If omega is any, so if I take the 2-cross disks here, let's make it a bit bigger. If omega is any balanced pseudo-convex set containing these 2-cross disks, then it has the isometric extension property if and only if it's contained in the diamond. So the diamond is this kind of envelope here. So if I choose omega to be this set, that works. And if I choose omega to be this set, it fails because of this bulge. Oh, my second choice of omega is bad. Sorry, that's not a good choice because it's not balanced. But you get the idea that you have this within the realm of balanced sets. You clearly, if you can extend it to the diamond, you can extend it to any subset of the diamond. So anything smaller is okay, and nothing bigger works. If you drop balanced, it gets more complicated. If you drop balanced, then well, there is a theorem. We showed that if omega is any domain of holomorphy, so that the pair omega t has the isometric extension property, then t has to be relatively closed in omega, and then you need to be able to define omega as an intersection of a bunch of inequalities. And if you think about it, what this inequality says is if I choose the function lambda goes to tau 1 lambda 1 plus tau 2 lambda 2, we know that has norm less than 1 on the 2 cross disks T. And then this says that I can find some extension to all of omega. It has to agree with this function on these 2 cross disks. So a general extension means I can add any function C that vanishes on the 2 cross disks. I can pull out a product lambda 1, lambda 2. And so then this inequality for any particular lambda just says that this function extends. So the content of the theorem really is if I can extend all these linear functions without increasing their norm, then I can extend everything. Yeah, that's what I just wrote here. As long as I can extend the linear functions, then I can extend everything. But with that in hand, you can show that there are sets omega such that the pair omega t has the isometric extension property, but omega is neither contained in the diamond nor is the diamond contained in omega. What kind of t? So I'm assuming here t is always these 2 cross disks. T is always d cross 0 union 0 cross d. And then I'm asking, so given this, for what omega does omega t have the isometric extension property? And I said that there's a maximal balance such set, namely the diamond. But here's a concrete example which satisfies the theorem 3. So it has the isometric extension property for this particular choice omega. And you can check that this set omega is not a subset of the diamond nor a superset of the diamond. So if you drop balanced, you no longer have a maximal set. Okay, so Walter Rudin asked in 1969 in his book on function theory on polydisks, that if you have any pair omega v, which has the bounded extension property, so that's kind of like the isometric extension property, except you're allowed a constant. In other words, you want to know that given every bounded analytic function on v, you can extend it to some bounded analytic function on omega, though perhaps your norm is larger. So he asked, if you can do this, can you always do it with a linear operator? And to the best of my knowledge, this question is still unanswered. But if you ask for the isometric version of this, then the answer is no. So I showed how to extend functions from these 2 cross disks to the diamond, and it was linear provided the functions vanished at the origin. But if they don't vanish at the origin, you have to compose with a Mobius map on the range to force them to vanish at the origin. and that messes up linearity. So that particular choice doesn't work. And in fact, you can prove that there is no linear isometric extension operator from the bounded functions on the two-cross disk to the bounded functions on the diamond. If you insist on linearity, you can still do it, but the price you pay is you have to shrink your domain. There's a smaller domain on which there is a linear extension operator. Okay, so we made quite a lot of progress in understanding this particularly simple example of the two-cross disks. And there are some other sets that one can analyze. For example, here's a two-dimensional set in C3. I take the set of points in the tri-disk that satisfy Z3 squared is Z1 times Z2. I'm not quite sure why I said this. There's a branched cover of the bidisk inside the tri-disk. I guess you have two copies of the if you think of Z1, Z2 as kind of the basis, then you have two copies of that inside the tri-disk branch of the origin. So then you can ask, well, this is a set, so we know that there's some three-dimensional set for omega such that the pair omega V has the isometric extension property. Can we say what they all are? Well, I claim that in some sense we can. Namely, I take the set G defined by this weird looking inequality. The modulus of Z1, Z2 minus Z3 squared is less than 1 minus the modulus of Z3 squared plus the product of the square roots of 1 minus Z1 modulus Z1 squared and 1 minus modulus Z2 squared. That's a pretty strange inequality. But this is a bona fide open set in 3 dimensions. And moreover, you can show that it's convex. You can show that the pair GV has the isometric extension property. And it's maximal, again, if you impose the requirement of being balanced. So just like the diamond was the maximal balanced set for which the pair of cross disks had the isometric extension property, this set G is the maximal balanced set for our set here, V. Now, the proof heavily uses operator theory. So I would challenge function theorists to come up with a proof of this fact without using operator theory, because the statement has nothing to do with operator theory. This is just a statement about functions. Let's see. So let me close with some questions. First one is linearity. So suppose V is any analytic set. We know there's always some domain omega such that the pair omega V has the isometric extension property. And we know that when this happens, you can't necessarily do it linearly, but can you do it linearly if you shrink omega? So if V is an analytic set, is there always some skinny domain omega containing it so the pair omega V has the linear isometric extension property? Second question I want to ask is about complete isometric extensions. So you can, a complete isometric extension property is the same thing as the isometric extension property, except now you look at matrix valued functions. So I start with, oh, so it was called F, the original thing. So I start with F from omega to the n by n matrices. sorry, not from omega, from V. And I want to know, I want to find a phi from omega to the n by n matrices such that the sup over omega of the norm of the n by n matrix phi of z is the same as the sup over V. So if I can do this for all n, then we'll say that the pair omega V has the complete isometric extension property. And just as in the scalar case, you can prove that given any V, there always exists some omega so that the pair omega V has the complete isometric extension property. What we don't know is, do you have to shrink? In other words, if you know you have the scalar isometric extension property, do you get the complete isometric extension property for free, or do you perhaps have to shrink down to a smaller domain to get this stronger conclusion? And then I can't completely get retracts out of my mind. Suppose we come back to the tri-disk. Suppose I have some set V inside the tri-disk that has the isometric extension property, and V is relatively polynomially convex. Does this force V to be a retract? Now, in the tri-disk, if you remember, thanks to the Heath suffrage result, we know what retracts look like. They're graphs of functions, either a graph of a function of one variable or a graph of a function of two variables. So they're much more tractable than in a general domain omega, where nobody knows much about retracts. And finally, a very concrete question. The simplest example we don't know the answer to is I take this particular set in the tri-disk, the set where Z1 plus Z2 plus Z3 is equal to Z1 Z2 plus Z1 Z3 plus Z2 Z3. So that's a two-dimensional set inside the tri-disk. Does the pair D3V have the isometric extension property? This is the simplest case we don't know the answer to. Okay, I'll stop here. Thank you very much.
Thank you. Thank you. No questions.
I have a question, John.
Yeah.
If instead of looking at complex varieties V, can it be done more generally with replacing complex varieties V by Cauchy-Riemann varieties?
Certainly the question makes perfect sense there. I haven't thought about it, so I can't say anything intelligent, but yeah, that's a very natural question. I'm afraid I can't tell you anything about it.
Oh, thank you, John. Thanks for the talk.
Oh, you're welcome. So Bill asked a question, how does operator theory come into Theorem 6? And the answer is our weird set G, which I defined using an inequality. Let's see, where's G? You can also, and this is where the operator theory comes in, you can show that G is the set of triples Z1, Z2, Z3 with the property that for every unitary U, which if I write a unitary matrix in a block form here, so U is a 2n by 2n matrix that I write as A, B, C, D, then if U is unitary, then if I look at Z1A Z3B, Z3C, Z2D. So I look at this new matrix, which I multiply A by Z1, D by Z2, and B and C by Z3, that this is always a contraction. And this condition, saying this is true for all unitaries, translates into this inequality.
Thanks.
Do we have a pick theorem on H infinity of the two ball? Not a good one. No, there's so you'd like to say that on H infinity of the ball, I give you a finite. So the question is a pick theorem on H infinity of the ball. So that would be some characterization given lambda 1, lambda n in the ball, W1, Wn in C. When does there exist some phi that maps the lambda j's to the wj's? That's an arrow. And the norm of phi is less than or equal to 1. And you'd like to check that by checking some sort of finite number of conditions. And there's there is some theorem along the lines that if I look at 1 minus wi, sorry, 1 minus wi wj bar times some kernels lambda I lambda j, you can check that if this holds for a very, very large collection of kernels K, that's a necessary and sufficient condition. But the set K is so large that checking it is kind of impractical. So no, there's no, I would say there's no effective pick theorem for the two ball. No. It's almost a tautology that if I make my set of kernels large enough, this can be a necessary and sufficient condition on any domain. But what's interesting in the disk and the bidisk is that you can cut down the set of kernels to something manageable.
Other questions?
Oops.
Well, if not, then let's thank our speaker once again. And we'll see you all next week.
Thank you very much.